This GIF shows a crash test and a dummy inside. Crash tests like this are very important, especially on the assessors or the public safety assessor to determine if the safety mechanisms of a certain vehicle is at standard. And those safety mechanisms can either be the airbag as well as the um, seatbelt. Now, engineers understand the mechanisms on how passengers would be safe inside the vehicle, especially when accident happen, because of their understanding of our topic for today. That is the Newton's laws of motion. So for today, our objectives are the following. We are to identify the different types of forces. We are to draw free body diagrams, and we also have to state and explain the different Newton's laws of motion, as well as give factors affecting motion. In our previous topic, in kinematics, motion can be described using words, graphs, diagrams, numbers, etc., without identifying what causes those descriptions. Meanwhile, Isaac Newton explained why objects move or do not move, as they do using his law of motion, in the branch of mechanics which is called dynamics. So dynamics explains why objects move or do not move as they do obey the laws of motion. These laws have become known as the Newton's laws of motion, included in his book Principia. Newton's laws of motion consist of three different laws. The first law is the law of inertia, the second law is the law of acceleration, and the third law is the law of interaction. In this framework, we are going to see how forces affects motion, what are the different types of forces, contact and non-contact, and what are the different specific forces under those types. We're also to understood the different laws of motion, as well as what do we mean when we say initial frame of reference. Let us start. First, the person behind the Newton's laws of motion. So it's Sir Isaac Newton. He was born on December 25, 1642. He was an English physicist and a mathematician. His studies was very vast, ranging from optics, motion, planetary motion, and gravitation. He was knighted by Queen Anne of England, and he is actually one of the head of the Royal Mint. So before we understand what do we mean when we say the the law of inertia, law of acceleration, law of interaction, we have to understand first the vector quantity that we are going to use all throughout, and that is the force. So what is a force? So a force is simply a push or a pull, either microscopic, either in terms of atoms, molecules, or large objects such as planetary objects such as the moon and the earth. The force will still either be a push or a pull upon an object, resulting from the object's interaction with another object. Whenever there is an interaction between two objects, there will be a force upon each of the object. When the interaction ceases, kapag nawala ng interaction, the two objects will no longer experience the force. Remember that force only exists because of an interaction. So there are two types of force, namely contact and action at a distant force. So for simplicity's sake, all forces of interaction between objects can be placed into these two broad categories. Contact forces are those types of forces that result when two interacting objects are perceived to be physically in contact with each other. Examples of contact forces includes frictional force, tensional force, normal force, air resistance, and applied force. Meanwhile, action and distance force are those type of forces that result even when the two interacting objects are not physically in contact with each other. Yet, they can exert either a push or a pull despite their physical separation. Examples of action at a distant force include, of course, gravitational forces. For example, the sun and planets exert a gravitational pull on each other despite their large spatial separation. Even when you feet, even if your feet leave the earth and you are no longer in physical contact with the earth, astronauts can still feel the gravitational pull between them and the earth. Electric forces are also action at a distant force. For example, the protons in the nucleus of an atom and the electrons outside the nucleus experience an electrical pull towards each other despite their small spatial separation. Magnetic forces are also action at a distant force. For example, if you have two magnets with you, they can exert a pull on each other even when they are separated by a distance of a few centimeters. There are other examples of a contact and an action at distant forces that is listed on the AGHAM website. Kindly check it out. So these are the different types of forces. Let's analyze each of them. First is the applied force here on the first image here. So the applied force is, of course, is a force that is applied to an object by a person or an another object. If a person is pushing a desk across the room, then there is an applied force acting upon the object. The applied force is the force exerted on the desk by the person. So this applied force can either be a push or a pull. Pwede. Next would be gravitational force, this one. So the force of gravity is the force which the earth, the moon, and other massively large object attracts another object towards itself. By definition, this is the weight of the object. All objects upon earth experience the same amount of force that is directed downward towards the center of the earth. The force of gravity on earth is equally always equal to the weight of the object. You may use F grav is equal to mg, whereas m is the mass of the object and g is the gravitational pull. I think we have already done this in our free fall problems. Next one is the normal force here. So the normal force is the support force exerted upon an object that is in contact with another stable object. For example, if a book is resting upon a surface, for example, this one, here, if the book is resting upon the surface, so it will exert a force downward. However, in order to support the weight of the book, on occasion, a normal force is exerted here on top of the book to counteract that force, which is this red one here. For example, or for instance, if you lean on a wall, the wall actually pushes you horizontally. That is the normal force. It's a special type of force because it only acts if something also acts upon it. Next one is the friction force. The friction force is also another type of a special force. Again, it won't act unless acted upon. The friction force is the force exerted by a surface as an object moves across it or makes an effort to move across it, such as on this image. So this is the friction force. There are at least two types of friction force, sliding and static friction. When we say sliding, an object is already moving. When we say static friction, that is the friction you need to overcome for an object to move. For example, if this guy is just starting to push this heavy box, para gumalaw to, he needs to overcome the static friction. Though it is not always the case, the friction force often opposes the motion of an object. For example, if a book slides across the surface of the desk, then the desk also exerts a friction force in the opposite direction of the motion of the book. Friction results from the two surfaces being pressed together, causing intermolecular attractive forces between the molecules of different surfaces. As such, friction depends upon the nature of the two surfaces and upon the degree to which they are pressed together. Meaning, if a surface is smoother, it will have less friction. It will also depend if how heavy an object is. The maximum amount of friction force that a surface can exert upon an object can be calculated using the formula F, let me use a different ink. F friction is equal to the mu, it's called the coefficient of friction, multiplied by the F normal. So, what does it mean? U, or the coefficient of friction, simply means gaano kagaspang yung isang bagay. And F normal, this one here, is how much that object here, for example, how much this surface oppose the weight of the object. Next one is the air resistance. The air resistance is a special type of frictional force that acts upon objects as they travel through the air. The force of air resistance is often observed to oppose the motion of an object. This force will frequently be neglected due to its negligible magnitude. Minsan kasi super liit lang. And because it is mathematically difficult to predict its value. It is most noticeable for objects that travel at high speeds, such as a skydiver or a downhill skier, or for objects with large surface areas. That is why often parachutes here, they extend up to a large areas to create more drag. So air resistance is also called drag. Next one is tensional force. So tensional force is a force that is transmitted either through a string, a rope, a cable, or a wire when it is being pulled tight, such as this one, this tug of war. So since the player here pulls at this direction, this rope will experience a tensional force. The tension force is directed along the length of the wire and is pulled equally on the opposite ends of the wire. So for example, if the players here pulls in this direction, actually there's also a tensional force here on the other side. Last one is a spring force. So spring force is the force exerted by a compressed or stretched spring upon any object that is attached to it. An object that is compressed or stretches a spring is always acted upon by a force that is restored the object to its rest or equilibrium position. Meaning, after the spring is stretched, it will have to go back to its equilibrium position. For most springs, they obey the Hooke's law, whereas the magnitude of the force is directly proportional to the amount of stretch or compression of the spring. Okay, so these are the different types of forces, but there are other more, again, stated a while ago, electrical forces, magnetic forces, and we also have the fundamental forces, but we're not going to dwell more on those types. We'll now proceed with drawing free body diagrams. So free body diagrams are diagrams that are used to show the relative magnitude and direction of all forces acting upon an object in a given situation. If you can recall, on our previous scenario, we called that step the illustrate phase. Yung lagi natin dinodrawing through arrows through vector arrows specifically, we are still going to use that concept. Same as our previous quarter, the size of the arrow in a free body diagram reflects the magnitude of the force. The direction of the arrow also shows the direction of the force is acting. Each force arrows in the diagram is labeled to indicate the exact type of force. Again, dapat may label. It is generally customary in a free body diagram to represent the object as a box and to draw the force arrow from the center of the box outward in the direction that the force is acting. An example of a free diagram would be this one. Let's try to answer it. So on our first example here, we have a book rather that is at rest on a tabletop. Again, we can illustrate the object para di na yung problema sa pagdodrawing as a square, and we'll try to illustrate what are the forces acting upon it. If it's a book on a tabletop, let's draw the tabletop here. Here. What are the forces that will act upon it? First, since it's on Earth, Earth will have to pull it towards it. And that is the force of gravity. So don't forget the label. We're going to write here Fg. And again, since it is resting on the tabletop, what will happen here is that something would have to negate this, and that will be the normal force. Okay, so this book here doesn't move to the left or the right, which means these are the only forces acting upon it. Drawing free body diagram is very important because it allows you to visualize what are the different forces that interacts with each other. Let's have another example. A gymnast is holding onto a bar and is suspended motionless in mid-air. The bar is supported by two ropes that is attached to the ceiling. We have to diagram the forces acting on the combination of the gymnast and a bar. So let's draw first the gymnast as a square. So that if that is the gymnast and it's suspended motionless, supported by two ropes, from the term here itself, two ropes, which means we're going to have two forces here. But what type of force? First, of course, if it's suspended motionless in midair, gravity will again act upon it. So we'll write Fg. And since we have ropes here, which means ropes is tension. So which means we have here F tension 1, then F tension 2. Okay, and that's it. Those are the different forces acting upon this second example. Remember that objects do not necessarily always have four forces acting upon them. Di laging apat. There will be cases in which the number of forces depicted by a free body diagram can be 1 or 2 or 3. There is no hard and fast rule about the number of forces that must be drawn in a free body diagram. The only rule for drawing free body diagram is to depict all the forces that exist for that object in the given situation. Thus, in constructing free body diagram, it is extremely important to know the various types of forces. So you have to memorize yung table na pinakita natin kanina, yung different types of forces. Because it will allow you to describe physical situation. So we have to begin first in your understanding of the different force types to identify which force are present. Then determine the direction in which each force is acting. Finally, you draw a box and add the arrow for each existing forces in appropriate direction. Label each force arrow according to its type, and if necessary, you have to refer to the list of the forces and their description to further understand the various type of forces and their appropriate symbols. We'll now proceed with Newton's first law of motion. So the first law of motion, as a review, states that an object at rest will stay at rest, and an object in motion will stay in motion with the same speed and in the same direction unless acted upon by an outside force or an unbalanced force. So for this, if you can recall on your mini task 1, this is the part where you have answer part 1. So let's try to answer very roughly. So what you did is you try to apply a force of 15 Newton right to the box, and then you try to describe the motion using physics terms. And you have to refer to the speedometer in your answer. And then rough answer for this would be that as you apply, if you can recall, what happened there is that as you apply the 15 Newton force to the right, the box is displaced and moves at an increasing velocity in the same direction of the applied force. The box also accelerates to the right, meaning if this is the box, then you push it rather, you push it ng tuloy-tuloy, meaning you applied a force, it will also accelerate to this direction, right? The acceleration is also at that direction. For number 2, or letter B, you now reset the scenario and then you apply a force 15 Newton to the right for about 5 seconds. Then you reduce the applied force to 0. Do not reset the scenario, and then you are to describe still the motion of the box. So recalling what happened there is that the box moves to the right with the same motion as letter A, right? It still moves papunta dito. However, when the man stopped pushing, after 5 seconds, the box continues to move. Okay, so that's what happened there. Again, what happened is that you push the box, it moves, then you reduce the applied force. However, the box still is in motion. Afterwards, you apply a force 15 newtons to the left. Then you are asked to describe the motion. So what will happen there is that if you then apply a force of 15 newtons to the left, in the opposite direction, the box momentarily stop, right? So again, it's moving or accelerating in this direction. However, you apply a force in the opposite direction here, then it will stop, right? It will momentarily stop. Momentarily stop. However, if you keep on applying the same applied force, what will happen is that this box, which is moving to the right a while ago, will now start accelerating to the left. So that's what happened. Okay, so in order for you to exactly make the box come to a stop, what we need to do is that we have to push the box to the left or the right and immediately apply a force equal to the previously applied force and then release instantly. Okay, so I hope you can imagine. Meaning, tatansyahin nyo. For example, you apply a force of 15 newtons to the right, and then you instantly you apply a force 15 newtons to the left, and then release it. So bibitawan nyo. Pag apply ng 15 newton, bitawan, and that will make the box stop. Okay? So this scenario here is actually what proves the first law of motion. Remember that the box remains in motion even though the man stopped pushing, right? It still moves. And then the box will only stop if we apply yet another force. The box is at halt before the man pushes the box. So imagine here one. In this scenario here, if the forces are balanced, according to the Newton's first law of motion, if the forces are balanced, there are two conjunctures. or two clauses. First, if the object is at rest, and then the other one is if the object is in motion. Remember that the first law of motion states that an object at rest stays at rest and an object in motion stays in motion with the same speed and the same direction unless acted upon by an outside force. There are two clauses or parts to this statement. One is what predicts the behavior of moving objects, is one. And then the other one is what predicts the motion of an object which is already at rest. If we try to think about it in our everyday life, you can experience what we call inertia. Okay? If an automobile suddenly brakes, the force of the road on the locked wheels provide the unbalanced force to change the car's state of motion. Yet, there is no unbalanced force to change your state of motion. Thus, you continue in motion, sliding along the seat in forward motion. So, you jerk forward, tumatalsik ka. Okay? So, that is what we mean by this one. It means that if an object here is at rest, there is no force. There is no force, and if there is no force that will actually move it, it will stay at rest forever. Meanwhile, if an object is already at motion, meaning for example this volleyball, if it's already at motion, neglecting friction force, it will actually move infinitely unless something stops it. So you can see here, that is the same explanation a while ago. Remember that forces don't keep objects moving. Isaac Newton built on Galileo's thoughts about motion. The Newton's first law of motion declares that a force is not needed to keep an object in motion. Again, that's what we have said a while ago. For example, we have the ball in motion on a tabletop. It does not come to a rest position because of the absence of a force. Rather, it is the presence of a force. That force being the force of friction that brings the book or the ball rather to a rest position. In the absence of a force of friction, this ball will continue in motion with the same speed in the same direction forever. A force is not required to keep moving the ball in motion. It is the force that brings the book to a rest. So why does it seem weird that is actually the case in a moving object? Bakit ang hirap ma-digest that in that there's no force needed to keep a moving object still moving? Well, primarily because um, we live in a life of cause and effect. We think if something is happening, then something must cause it. However, in terms of physics, it's just the law of nature, just what it is. So going back to our first image I have shown you a while ago, how does this crash test um, uses or utilizes the knowledge of in terms of the first law of motion? Okay, let's have here and let's draw a free body diagram in terms of this scenario. First, remember that we have two objects here. First is the car, and then the other one is the person. Let's draw first the free body diagram of the car. So let's just, in a rough scenario, let's just state that the car, let me write it down. This is the car. It have a force here that moves it towards the left. However, we have here a lamp. So the lamp apply a force to this car towards the right. So what will happen here is that magkakaroon siya ng force here. Another applied force. Now, as you can see here, we have two applied force, and then they will have to cancel out each other. So if they cancel out each other, what will happen is the car will stop. As you can see here, it stops. However, if we now try to analyze the FBD of the person, so of course, the person is in a car, and it will also experience the same force because it's moving in this direction. However, as you can see here, it's not directly affected by the lamp. So what will happen is this force here will still continue to cause acceleration at the same direction. And this is where seatbelts and airbags come in. So because airbags or seatbelts will now seatbelts will now cause this force here to be cancelled as well. So that's how those safety measures are being utilized. We are now to proceed in the Newton's second law of motion. So the second law of motion states that the acceleration of an object as produced by a net force is directly proportional to the magnitude of the net force in the same direction as the net force itself and inversely proportional to the mass of the object. For this one, we have answered the, the following. Of course, this answer will differ. However, your answer should be following the same pattern. That as you increase here the force, you decrease the time. Okay? And if you decrease the time, it means you have increasing acceleration. Let me change the color. Okay? Acceleration. Okay. So again, if you increase the force, what will happen is that you're going to decrease the time. Decreasing time means you are moving quicker or faster, which means you have higher acceleration. Simply put, it means that the higher the force, the higher the acceleration. Going back to our definition a while ago, force is directly proportional to acceleration. Let's now proceed with number 2. This time you are to analyze the masses of the different objects. For this, I ask you to use a constant force, so that will be the constant in the formula. But for this, what you are to try to find out is the relationship between the mass and the acceleration. The garbage can create in the fridge, per logic, means increasing mass. And as you can see here, we have from top to bottom, we have here decreasing speed, which means we have also decreasing acceleration. Okay, which means, simply put, that if an object has a higher mass, we have lower acceleration, which makes sense because a higher acceleration ay a higher mass rather, mas mabigat yung isang bagay. It will be harder for you to accelerate it or to push it. So for the Newton's second law of motion pertains to the behavior of objects for which all existing forces are not balanced. A while ago, we have discussed forces if they are balanced. The second law states that the acceleration of an object is dependent upon two variables which you have observed based on your mini task 1. That is the net force acting upon the object and the mass of the object. The acceleration of an object depends directly upon the net force acting upon the object. Meaning, the higher the force, mas malakas yung pagtulak mo, the faster an object will accelerate. And as the force acting upon an object increase, the acceleration of the object also increase. And as the mass of an object is increased, the acceleration of the object will decrease. So that's what it means. So for the equation, the Newton's second law of motion can be formally stated as follows: that the acceleration of an object as produced by a net force is directly proportional to the magnitude of the net force. That's why this one, F net, is directly proportional to A. However, if that is only if the direction of the net force is also the same as the direction of the acceleration. And it's also inversely proportional to the mass of an object. This verbal statement can be expressed with the following formula: F is equal to ma. I think you're already familiar with that one. The above equation is often rearranged to a familiar form, and then the net force is equated to the product of the mass times the acceleration, which is equals to F is equal to ma. Okay, so that's it. Kung ayaw nyo tandaan, you can also use the triangle. Force is equal to mass times acceleration. You're searching for acceleration, you have to divide force and mass. So paulit-ulit lang yun. I think it would be easy for you to compute that one. Okay. So here's some problem solving. And we are to use our knowledge a while ago. Let's have some practice here. So we are searching for acceleration. So that is acceleration. That is force divided by mass. So that will be 10 divided by 2, giving us 5. Same as this one. 20 divided by 2 will give us 10 meters per second squared. The next one, 20 divided by 4 will give us 5 meters per second. Meanwhile, if we are now searching for the net force, we are to use F is equal to ma. That will be mass multiplied by acceleration. That's 2 multiplied by 5, giving us 10. Meanwhile, if we're searching for mass is simply equal to the force divided by the acceleration. Go back to the triangle, so that will be 10 divided by 10. That will give you 1 kilogram. For number 6, acceleration is equal to F is equals to m. That's 20 divided by 4. I think we have done that already. It's number 3. This will be 5. Meanwhile, for this number 7, S is equal to ma. That will be 5 multiplied by 100. That will give us 500 newtons. Okay, remember that the unit for force is again N, the unit for mass is kilogram, and the unit for acceleration is meters per second is squared. Remember that the Newton's second law states that the acceleration of an object is produced by a net force is directly proportional to the magnitude of the net force and is the same as the net force and is inversely proportional to the mass of the object. For the last and the third law of Newton, it's Newton's third law of motion. States that for every action there's an equal and opposite reaction. Now, this statement means that in every interaction there's a pair of forces that are acting and interacting on the same object. The size of the forces on the first object is equal to the size of the forces on the second object. The direction of the force on the first object is opposite to the direction of the force on the second object. Remember that forces always come in pairs. Equal and opposite action and reaction force pairs. To understand this better, we have here some examples. For example, the action-reaction in terms of a gun recoil. When a gun is fired, the gun itself recoils backward because of the reaction of the bullet as it leaves the gun. Similarly, the nozzle of a big fire hose, for example, you have a fire hose, has handles which firefighters must grasp firmly because as the jet of water shoots out of it, the hose itself is forcibly pushed backward. The same thing happens in the dynamics of a rocket propulsion. The rocket's action is to push down on the ground with the force caused by its powerful engines. And the reaction is that the ground, quote unquote, also pushes the rocket upwards with an equal amount of force. And that's it for the different Newton's laws of motion. Let's recall, the first law of motion states that an object at rest stays at rest and an object in motion stays in motion with the same speed and the same direction unless acted upon by an outside force. For the second law of motion, that the acceleration of an object as produced by a net force is directly proportional to the magnitude of the net force in the same direction as the net force and inversely proportional to the mass of the object, or F is equal to ma. For the third law of motion, that is the law of action-reaction that states that for every action, there is an equal and opposite reaction.